It's a long chapter. It's not the longest in the textbook, but it's the longest chapter we deal with in this textbook in Thermo 1. So we'll talk about entropy being a property. It's a new property. We're familiar with other properties as well. We'll talk about its datum point. Where do we start the measurements of entropy for? Entropy, that property, where do we start its measurement from? We'll talk about popular diagrams. We had the pressure volume diagram. We had the pressure temperature diagram. Now we'll add the temperature entropy diagram and the enthalpy entropy diagram. We'll also talk about how we can relate this new property to previously existing properties through the TDS equations. Equations to relate properties to other properties, the new property, entropy. And then we'll show how to calculate the change in entropy for an incompressible as well as an ideal gas. We'll take a look at using this property diagram, the temperature entropy diagram, and interpreting the area under it. How did we interpret the area under the PV diagram? Work. The area under a TS diagram, or the curve on a TS diagram, can be interpreted as Q. If it's internally reversible, if it's a special process, the internally reversible process. We'll then do entropy balance, just like energy balance, for closed systems. Then we'll do entropy balance for open systems. Then we'll talk about special processes. A new term, we had isothermal, we had isobaric, we had isochoric, now we have isentropic. That property which is constant during an isothermal was temperature. Isobaric, constant pressure. Isochoric, constant volume. Isentropic, constant entropy. And then we'll talk about efficiencies. We can compare how well a turbine does to the perfect, frictionless, completely reversible turbine. So we'll have isentropic efficiencies for turbine, for a nozzle, for a compressor, for a pump. They're very similar, but we have efficiency measures. And then we'll talk about something very abstract at the very end. We'll talk about the heat and work transfer for an internally reversible process where you have flow through a device. And let's just leave the best to last. I'll try and explain that later. I probably shouldn't try to explain the whole chapter to begin with, right? How do you eat an elephant? One bite at a time. How do you define temperature? How do you define temperature? That's a good question, I think. Not how another book defines temperature, but how do you define? And then how do you define time? If I wanted to embarrass y'all, right, I'd just say, write down a one-sentence definition of time, and I'll come around and grab a few random, and I'll read it out loud. It would be embarrassing. I don't think I could do a very good definition of time. Time is a concept everyone is familiar with, but it's a little bit abstract. I know how it's measured. I always look at the clock. You know when you're getting out of this class. We know when the semester ends. All right, so time. Energy is a familiar term, but it's only more familiar because we use it like time. But if you had to define energy, we already did it before. I gave a definition. I believe it was something like the energy is the ability of a system to have an impact or making a change or making an effect, cause and effect on something else. That's what energy is. And then entropy. Ooh, hey, professor, I'm having a hard time understanding entropy because you're a bad instructor and you're not defining it clearly. Well, guess what? Entropy is a lot like time. Temperature is a little easier. Things hot and cold, right? Hot, it's a measure of the hotness or coldness of an object. That's what temperature is. Time, I'm gonna punt. You define time. All right? Maybe I'll ask you to give me your submissions of time. I know what somebody's doing right away. I want to Google it. Give me the definition of time. But entropy, I'll give you a quick one. It's basically a measure of disorder of a system. Measure of disorder. Okay, entropy is a property of a system, just like energy is a property of a system. Is energy a property of the system? Yes, it is. That's what energy is. Entropy is just like it. Entropy is abstract, just like energy is an abstract concept. It's challenging to get to be very clear and very succinct in the definition of these terms. And when you do, when you package it finally down to a few words, it's like, oh, wow. You know, a few years ago, everything was mission statements. Anybody ever seen the mission statement of UTSA? It's out there, but it kind of loses its punch, you know, because it's down to one sentence. You know, this is our purpose, UTSA. Okay, well, trying to get everything simplified and discussed that way. Okay, energy is the ability of a system to cause an effect, to do something. That's my definition. It's paraphrased from other definitions. Entropy is a measure of the disorder of the system at the molecular level. That's a definition. That's a description of it. You know what? We really don't build on that definition. It just helps give you a warm, fuzzy feeling for what it is. All right? All right. In general, a system, if it consists of, let's say, 1 kilogram of matter, entropy is lowest when in the solid phase. Then it's higher. The entropy increases when it's in the liquid phase. And the entropy is highest if you had a kilogram of that substance in the gas phase. That's a general trend. And so what you have is it gets increasing entropy. And you say solid, liquid, vapor. It's a measure of something that goes up when you go from solid, liquid to vapor, molecular disorder. Notice it's really closely related to temperature, but it's not solely dependent on temperature. Entropy is not solely dependent on temperature. A quantity is a property if and only if its change in value between two states is independent of the process. Do you remember something like that? Did we talk about this before? What is a property? A property, a quantity, a characteristic of the system, a quantity like that, is a property if and only if the change between two states is independent of the process. It just depends on the endpoints, not on how you got between the two states, right? Somebody says, I started this morning at my house. I got my car and I drove to UTSA, right? I can tell you the distance between their home and UTSA, parking lot to parking lot, but I can't tell you how far they drove. They could have gone to visit a friend, pick up a friend. They could have driven somewhere. The path I'm not certain of, but I know the distance between the parking lot to parking lot, a property, okay? Make a list of those properties. You should be good at this. Put it the pressure, temperature, specific volume, internal energy, enthalpy, and finally now entropy. We have other properties. We had some specific heats, right? C sub P, C sub V, ratio specific heats. You have some other properties. The list gets very, very long. But these are our core in Thermo 1. So here's a property diagram. Maybe it's a pressure volume diagram. And we're initial state 1, and we go to final state 2. And if I do an integral along the path A, so here's path A. It goes from here to there. So if I do the integral along path A of the summing up, that's what integration means, summing up all the little differential changes in volume, what does that equal to? What is this integral along path A from initial state 1 to final state 2, integral dV equal to? What is it? How about something even easier? I'm going to uncover the box. No, you're making it too hard. Think simple. I'm talking about what is the characteristic of a property. What is the integral dV? It's just V2 minus V1. Does that equation make sense? That's a simple integral they didn't give you on the final exam of Cal 1, but you wish you had it. Professor, I don't want to memorize the integral of the arctangent, hyperbolic, sinh, whatever of x. I want to know the integral of 1 dx. Right? All right. So this is true, isn't it? Isn't that true? It's almost too easy. So what about that? Is the integral along path A dv is equal to the integral along path B dv. True or not true? It's true. The path, it's irrelevant. I'm trying to restate what I stated before. It's a property. So volume is a property. Let me ask this. We now introduce this cyclic integral. What does that mean? Over a cycle. I'm going to end at the same point or the same state that I started at. That's what the cyclic integral shows. And we're going to integrate volume. Could I make that the integral of A, then back C? Or could I have done it B, then back C? Either one of those loops or those cycles would work. And for each of those, the cyclic integral is 0. Does that make sense? So either path A and then C or B and then C, you get 0 for any and all properties. We just use a property diagram to help us visualize what the math is saying. So Clausius inequality. Hey, isn't that where we ended the previous chapter? Some guy, some great man in thermodynamics history, came up with this inequality. He said the cyclic integral, that's what this is right here, of del Q, that's the summing up of all the little heat transfers, divided by the boundary temperature at which those heat transfers are occurring. So it's del Q over TB. That sum over the cycle is equal to a quantity which is net negative. It's always going to be less than or equal to 0. And so what they do is they introduce a negative times this sigma cycle. This sigma cycle was a measure of how many irreversibilities there are in that real cycle. It's the strength of the irreversibilities. So if you had no friction, everything's internally reversible, 0. If there's some friction, it gets larger. So this gets increasing with the amount of irreversibilities. That's the Clausius inequality. Aren't you glad that some people lived a long time ago and were pretty smart and their life work can be summed up in something like this and it's useful to us today? Yeah, right? Now, what you do is you say, I want to do this for a cycle made up where all the processes in the cycle are int rev. What? Int rev? Oh, yeah. Internally reversible. Okay? If they're internally reversible, how does the Clausius inequality change? I lower the box. I scoot down to reveal more information. How's it going to change? It's 0 on the right-hand side. That's now our equation. Okay? It used to be an inequality that introduced negative sigma to make it an equality, and when it's internally reversible, sigma is equal to 0. So now we have this path integral. Can I describe this integral as the sum of 2? Can I say it goes along path A and then along path C to get back to point 1, state 1? Sure. And we already said that was 0. Guess what we're looking at? So just like what we did before. And then he made the observation, Clausius made the observation, you know what? That's a property. It has all the characteristics of a property. I'm going to call it a property and I'm going to give it a name. That's what Clausius did. So it doesn't matter if it's over path A to C, B to C, it's always equal to 0. And because of that, if these two parts right here are the same, guess what these two are? They're the same. As long as you are along an internally reversible path between, from 1 to 2 along path A or 1 to 2 along path B. Here's a picture of the man, the years he lived. Did he live a long time ago? He sure did, right? And so is one of the founders of modern thermodynamics, and he coined the term. He introduced the word entropy, and he said that's a property. That's a property. And so this new property, and I say new kind of in quotes, it's new to you, it's new to me. But it's been around, he coined it in 1865. I mean, try to put that in context. What was happening in the United States 1865? Bloodbath. You got it right. Big time. So we're studying something that's not that new. It's new to you, it's new to me, but it's been around for a long time. He said this integral looks like I can write it as a change in a property from point 1 or state 1 to state 2. Or a different, you can put it out as a finite change or an infinitesimally small change, either way. So this is the definition of a property called entropy. It doesn't look like it's related to a molecular level disorder, but that gives us a warm fuzzy feel for it. But this is how you define it. So take a look. What are the units on entropy? Right, you take a look and you say this is in kilojoules and this is in Kelvin, so it's kilojoules per Kelvin. And again, was there a physical explanation of entropy with this derivation from Clausius Inequality? No, there wasn't. So I've given you my best shot, and if you ask me for a better definition of entropy, I'm going to say, I will give it to you as soon as you give me a good definition of time. Have you ever heard of time? Yes, you have, so you should have a pretty good definition of time, right? All right. Let's change this to 1. 1 kilogram of water in a piston cylinder assembly is heated from saturated liquid to saturated vapor at a constant pressure. How do we do that? Well, we typically put the piston this way, put the weight on it, and let it rise in a frictionless cylinder. And so our fluid starts off down here, and that's our system. Okay, it's water, and it's at constant pressure. The pressure is always 0.5 megapascal. How many kilopascal is that? How many bar is that? All right. The process is internally reversible. A lot of times now we're just going to say this is an ideal process. It's internally reversible. Okay? Okay. It's heated from saturated liquid to saturated vapor. You know it's going to expand dramatically. I'm not going to try and show it expanding. Determine the change in entropy of the water. So what is S2 minus S1? Well, would that be the integral of del Q divided by TB? Int rev? Sure. Okay, tell me a little bit about the temperature that the heat is being transferred into or out of that water. It's a saturation temperature. Is it constant during this process? Yeah. Because it starts saturated liquid to saturated vapor. It's constant. Can that then come outside the integral 1 over T sat to integral del Q? Sure can. That's why we made up this perfect little problem. Okay? And so what is the integral del Q equal to? Is it equal to Q1 to 2? How much heat is transferred to make it go from saturated liquid to saturated vapor? So we jump over here and we say first law for this process. It looks like it's going to be the mass times U2 minus U1 is equal to Q1 to 2 minus work 1 to 2. Do you like that for a first law statement? Closed system, focus of the analysis is the water, and it's being heated. It's constant pressure. Can that be P V2 minus V1? Can I combine these and get Q1 to 2 is equal to the mass H2 minus H1? Little algebra. Yes? Warm fuzzy feeling? Or blank stares? Can I write this as HFG? What was HFG, name of it? Enthalpy change during the vaporization, so heat of vaporization, another way of calling it. So we can now put over here that this is equal to 1 over Tsat m times HFG. That will give us m times S2. State 2 was S of G. What was state 1? Saturated liquid, S of F. So S of G minus S of F. And what you can do is you can go to the textbook and you can grab numeric values for the saturation temperature. Let me grab a numeric value for that. The saturation temperature is 151.9 degrees C. Put in a mass of 1 kilogram. The enthalpy, heat of vaporization, 2108.5 kilojoules per kilogram. And you then put the 1 kilogram over here for the mass, 1 kilogram here. That really cancels on both sides. And you can then get SFG from this relationship. I made one error on purpose. What's my error? I need that temperature in Kelvin. I don't know how many times I'll repeat that when I teach a class like this. You know, sometimes you need the absolute temperature. It must be the absolute temperature. All right? This is one of those times when you deal with entropy, you need that absolute temperature. So I need to come in here and add 273.15, and that then converts it to Kelvin. True? And if you make that change, you compute on the right-hand side, you get something like 4.690593. Way too many digits, but there is kilojoules per kilogram Kelvin. Now I come over here, if I just look up S of F and S of G out of the table, I take the difference between 6.8212 and 1.8607. We get the same number. So things are consistent. Okay, things are consistent. Now, let me ask you this. How many digits did they give me for these S's? How many significant digits? 5. So I have the ability to write the answer on the left-hand side to 5 significant digits, or roughly. Now, they gave me this one to 1, 2, 3, 4, 5 for HFG. The temperature, I've got it to 4. Okay? But, you know, I really shouldn't push this beyond 4. But it's surprising that, you know, it's got agreement to 5 or 4 digits.
Switch to 9 and 6. Yeah, 4.69.
Whatever. Do the math. I think I wrote them down wrong. Which way is it? Take a break. You tell me.
Yeah, it's 9.6 is correct.
It's over here is 9.6. I wrote it down too wrong. Too fast. I wrote it down wrong because I was too fast. Thank you. All right. What is more important? The magnitude of the energy value at a particular state or the change in the energy between two states? Which one of these is more important? It's always a change in energy. It's not really the magnitude of internal energy because that depended on the datum point. Guess what's true also for entropy? Entropy values by themselves depend on that datum point. Where did you start the measurement? And the change in entropy is what's the important quantity. What is datum? I just used that word. Used it a couple of times already. You just Google it. You find the definition. It's the fixed starting point of a scale or an operation. That's what datum means. If you didn't learn anything today, here's your chance. Right? Datum. Nice fancy word. So, here's a question. Where is San Antonio, Texas located? Somebody might say, it's a little west of Houston, south of Dallas, whatever, right? They struggled with this when they were doing the navigation, and they actually had a big meeting come, and they voted on it, and they said, you know what? We know how to measure things from the Earth around what we call the equator. We could pretty well get a good sense of where that is. But they basically just arbitrarily picked this line. What do they call that line? And what city or place does it go through? You got it. Anybody ever been there? Really? Wow. Do you have your picture standing on the line? Wow, that's great. You can get your picture standing on the line. You say, hey, I'm on both sides. But anyway, they measure going this way is west, going that way is east, and then right over here is the date line, isn't it? The other side of the world. And so somebody just had to pick a datum point for measuring so we can tell where the location of San Antonio, Texas is. Everybody's got GPS and everything else. Just, I don't tell me what streets to turn at. Just give me your house's GPS coordinates and I'll get there. How many people do that now? They do. They just don't get bothered giving me directions. Just give me your GPS coordinates and I'll get there. And here is San Antonio. This is San Antonio. Hey, I went to the trustworthy source and to get it. The latitude and the longitude. So it's 29, almost 30 degrees north and 95, almost 100 degrees west. And this guy's plot that he made, which is really good, you can read it actually. You just start clicking it off. Here is 0, go up 10, 20, 30. So we're about 30 degrees north. Okay? 10, 20, 30, 40, 50, 60, 70, 80, 90, right at 100 west. And but it all depends on the datum, where you start the measurement from, true? All right. Go to the table. Go to the steam, right? Steam tables. And we have this column of entropy, the right units. Where's our datum point for steam? It's where it's 0. And so it's 0 at this temperature and pressure when it's saturated liquid. What point is that? I know the datum point, but it's also a different name for that particular point. The triple point. So they said saturated liquid is given a value of entropy of 0 for water at the triple point. That's for water. Do you think I can get a negative entropy for water H2O? How would I get it? I would freeze it. I would go look at some S values for ice in your tables, and you'll find negative entropy values. How about for refrigerants? So let's go to refrigerant R134A. Let's find where S is 0. S of F is precisely set to 0. That's not just some random thing. They chose it to be 0. At what temperature? Negative 40. Why negative 40? Well, it's pretty cold. We do refrigerate things and freeze things below that, but it's a special temperature where negative 40F is negative 40C, the same hot and cold. Okay. And they picked saturated liquid to have a entropy value of 0. Hey, what was the energy benchmark or starting measurement for refrigerants? It was the enthalpy of saturated liquids were set to 0. Can you have a negative H? Yes. Can you have a negative S? You sure can. You just have to get it colder. Go to propane. You have a table for propane. Oh, you know what? Some odd reason they can use propane at lower temperatures. Here is the datum point because it's used as a refrigerant. They picked 0. What are these values of S? Negative. You can have negative values of entropy. I'll be able to make a question on the final exam or third exam, and I'll try to explore that concept just a little bit differently and I'll get somebody to say, you cannot have a negative value of entropy. How many times have I just said you can have a negative property, the value of entropy, the property entropy can be negative? We'll find out. All right, notice also enthalpy. Can you have negative enthalpies? Sure can. Sure can. It's the difference, not the magnitude of energy as well as entropy that matters. We love these diagrams. So a temperature entropy diagram, somebody out there in some Wikipedia organization did a pretty nice plot. So here's degree C, here is entropy S, plotted this way, increasing. And what do they see? What do you see right here in red? A dome. That's the two-phase dome. Everything below it, you're in two-phase mixture, saturated liquid vapor. True? And then what do they have way out in here? Superheated vapor approaching ideal gas behavior. Okay, what do they have out in here? No lines. You can't get the material to be in that state. Okay? It doesn't exist. What you have is you have a lot of stuff tucked right in here. What's all in here? Compressed liquid, subcooled liquid. And notice they put in lines. The blue lines are constant pressure lines, and these are very high pressures, and these are very low pressures. And the constant pressure lines come down, they come hit, they go across in the two-phase region at a constant temperature. But you can have really high pressure lines, and that's just really compressed liquid in this region. All in this region, some supercritical state if it's not approaching ideal gas behavior. All right. The book has a better, as well as other illustrations of temperature entropy diagrams, but this one's pretty good. What are the red lines? They show the red line starting from this point way up here. What do you think the name of that point is up here? Critical point. All this line of x equal to 1. I forgot what x is. Quality. And so that's a sequence of states known as saturated vapor. And all of this, x equal to 0, saturated liquid. Right. And so you see that these are lines of constant quality in that dome. Well, that's our one property diagram, temperature entropy. And the next one actually is given a name, the Moly A diagram, after this person right here, Richard Moly A. And he's a great German physicist, applied mechanics. You can see the years that he lived, 1863 to 1935. Okay, so what Great War did he live through? Yeah, the big one, World War I, which wasn't the big one after all. It was followed by the second one. Okay, so but he made it through that one. Actually, I think in 1922 in Los Angeles, they had an applied physics thermodynamics conference, and they honored him at that physics conference in Los Angeles. And they said, oh, we passed a resolution. Professor Moly A, we appreciate all your hard work and recognize the value and contributions. And they raise their wine glasses or whatever, water bottles, and they clink them together. And they say, oh, we recommend that if there's ever an entropy HS diagram, enthalpy entropy diagram, we recommend that it be given your name, that your name be attached to it. Now, somebody could get together and they could do the same thing for a TS diagram, and they should call it the whatever persons, to honor somebody that did some work. So anyway, that's what happened. And so from then on, and it's stuck pretty well from that conference on, the Moly A diagram. So what does it look like? It's a harder diagram. Why? Because this critical point isn't at the top of the two-phase region. It's still the critical point, but the two-phase region is kind of skewed. You can see it right here. See it skewed in there? And the quality, a line of x equal to 100% is right here. And it goes along, and then it comes down, and then stops at the critical point. And the line of x equal to 0 goes like that, saturated liquids. So there's a critical point. It's not up here at the top. You can have a higher enthalpy at a state that's saturated vapor, but it's not at the critical point. That's just what the physics gives you. Okay? And you then have entropy, enthalpy, and you have out here the superheated region, compressed or subcooled liquid, supercritical, and this whole region kind of coming down in there. And that's all the two-phase region. There's another excellent illustration of this in your textbook. Ready for some hard questions? Ready? Which diagram has a more symmetric two-phase liquid vapor dome, the HS or the TS diagram? TS is much more symmetric. All right. What do lines of constant temperature look like on a Moly A diagram in the superheated region? Lines of constant temperature. Yeah, so what happens is you kind of make a little quick sketch. What was that diagram? HS diagram, right? And we have the supercritical over here, but out here is a superheated region. And what happens is lines of constant temperature. As you go further out in this region, it becomes what type of gas? Ideal gas. When it becomes an ideal gas, what do we know about ideal gas? 3 things. That's one of them. That's the second one. I think this one comes to play. What does that mean? What does H as a function of temperature mean? Enthalpy is not a function of temperature and pressure, but enthalpy is only a function of temperature. Let me ask this. Could enthalpy be a function of temperature and entropy, or enthalpy a function of temperature only in the ideal gas region? Only a function of temperature in the ideal gas. So what does the lines where you have constant temperature look? What do they look like out in the ideal gas region on an HS diagram? Straight up and down, or straight across, or a 45, one of those 3. I'm going to pause, and actually I'll save this. All right, so a lot of you got it correct by deduction as well as looking in the back of the book at the tables, right? So this is a line of constant temperature, meaning that anywhere along this line, you only have one value of H, even though S is changing, right? If I change temperature, I may go up in enthalpy, or I may go down in enthalpy. But in an ideal gas region, those lines of constant temperature are what we call horizontal flat. Now, as you move, they kick up like this as you move into the other region on the HS diagram, okay? So we did the HS diagram. What diagram do you think is next? Let me take a look at the next question. So the next question says, what do lines of constant enthalpy look like on a TS diagram in the superheated region? So make our diagram first. Temperature entropy diagram. Have the more symmetric dome, critical point. We're talking way out here in the ideal gas region. And we're talking lines of constant enthalpy, where H is equal to a constant. Are they like this? Are they like this? Like that? Lines of constant H on a TS diagram. That's right. So for that, in the ideal gas region, one temperature for that enthalpy. And if you change the temperature, you'd change the enthalpy. Or if you, vice versa, go up or down. Goes up or down. Now, as you move toward the region here, they kick up like this. okay, where it's not ideal gas. Ideal gas is this region of the superheated. Not all of the superheated region, it's part of the superheated region. Make sense? All right. Ooh, now we have a derivation of some math. How does this new property entropy, we know it's how it's defined. We even made some calculations with it. We know some plots and what it looks like plotted. But how do I get a relationship between it analytically in equation form and other properties? Well, here's our first TDS equation. Let's go ahead and derive it. What it says is, the temperature times a small change in entropy is equal to a small change in U plus P times a small change in V. Well, you start by doing a differential form of the first law. What does that equation look like? It looks like du equal to del, I'm going to put lowercase q minus del lowercase w. So it's a lowercase u indicating specific internal energy. Lowercase q, heat transfer per unit mass. Lowercase w, work per unit mass, right? Everything in here is something like kilojoules per kilogram in that whole equation, the SI units for it. Okay. Do you like that equation? Yeah. Do we like it? Okay, let's rearrange this equation and put del Q is equal to du plus del W. Algebra? All right. If I have an infinitesimally internally reversible process, okay, what is del W related to? Is del W equal to PdV? So we can replace right here P dV. Wow, du. All right. What about, it sure does look like we've lined up the right-hand side pretty well. But how does the left-hand side become TdS? Well, just like del Q is equal to PdV, you recall del W is equal to PdV. Del Q over T, if it's internally reversible, is ds. So we make the additional restriction that del Q is equal to TdS if it's internally reversible. All right, TdS. There you go. That's our first TdS relation. Okay, now this is a little abstract here, but this was a restriction to allow us to get that. But because because entropy is a property, once you have this relationship, you can relax the restriction. It has to be an internally reversible process between them, because this is just a property change, property change, property, a property change. So it really works for any change. Okay? It's a change in the property ds is equal to blah, blah, blah. How about the second equation, the second TDS equation? These may look a little abstract, these first and second TDS equations. And oh, by the way, there's not a third or a fourth. So we're at the end of this one, right after we finish here. But they are very backbone of how we build property relations, especially analytic relationships. Because I want to get, how do I get the change in entropy related to change in temperature and change in pressure and change in U and change in V. All right. To derive this one, start with the first TDS equation, which was, oh, I already forgot. Start with the first. Then what we do is we recall H. Is that the definition of H? Is that a good equation? From calculus, if I said, give me the small change in H, you'd say, give me the small change in U plus, and I'm going to use something rule on this product, because P could be a small change in P and a small change in V. Product, right? P dV plus VdP. What is that? Calculus. Does that make sense? And did we say that was a product rule? Somebody said product rule? Something like that? All right. So now what I do is I see du sitting right here. I'm going to replace that by dH minus pdv minus vdp. So that's what I did with the du. And we leave pdv, tds, and guess what we can cancel? That one. And we're left with the second TDS equation, dH minus VDP. Okay? Great. That was super. I'm glad we did it, Professor. How are we going to use this? Let's solve a problem first, and then we'll do some generic application or use of it, okay? So 2 kilograms of water in a piston cylinder assembly initially at 160 degrees C, 150 kilopascal undergoes what type of process? Isothermal compression process to saturate a liquid. So for the process, they tell us what the work is. Determine for the process the amount of heat transfer. And then determine the amount of entropy change. What I would do is I would organize all the information given in the problem. I know it's water. I know that the mass is 2 kilograms. Please don't forget those little tidbits of information. Often I find it's useful to write them down, even though they're restate the problem statement. And then I think about, state 1, and it has a temperature at 1 of 160 degrees C, the pressure at 1 of 150 kilopascal, the internal energy and the entropy at 1. Guess what I can do? 2 pieces of information, 2 independent intensive properties, fix the state, and then I flip through the tables, and boop, hopefully I'm able to evaluate by looking up those properties of 25, 95.5, 0.2 kilojoules per kilogram, and the next one is 7.4665 kilojoules per kilogram Kelvin. We undergo a process to go to state 2. Can I tell the temperature at 2? Isothermal compression. So guess what it is? I deduce it's 160. All right. They also say it's saturated liquid. You know, that piece of information and that piece of information pretty well allow me to get this piece of information, this piece of information, this piece of information, if I need those pieces of information, okay? I could have gotten V1 as well. Okay, let me just say I need U2. U2 is 674.86 kilojoules per kilogram, and S2 is 1.9427 kilojoules per kilogram Kelvin. Did the entropy go up or down in this process? It went down. Okay, it went down. All right. Is that because of friction? Is because of heat transfer. It's going to be transferred out. We'll learn later when we do an entropy balance. Entropy is transferred with heat. Entropy is transferred with heat. So we apply the first law. So the first law for this process gives us that Q1 to 2 minus the work 1 to 2 is equal to the mass U2 minus U1. Okay? So what do we have? We have that the heat transfer, the question for part A, is equal to the work which was given to us plus the mass times U2 minus U1, nothing to do with entropy, and we calculate that it's negative 4784 kilojoules. What does the negative sign imply? It's heat out of our system. And that's where the entropy is going. It's going with the heat out of the system. That's why the entropy is lower at state 2. But we'll get into more of an entropy balance. Now, what about the change in the entropy? Only way we can do it for this point is to use the integral del Q over T, internally reversible. We note that the temperature is constant. It becomes Q1 to 2. It doesn't always happen. It's just a special case. It's isothermal. It always stays at 160 degrees C. If it didn't, all bets are off. You can't use that equation. Next time we'll get to a more general entropy balance equation to solve more general problems. So you come in and you say, okay, well, what is that temperature? It computes to be 433.15. We just computed the heat transfer, negative 4784 kilojoules. And so S2 minus S1, we compute it to be 11.04 kilojoules per Kelvin. And then if you go and evaluate this minus this and multiply by 2 kilograms, you get the same number. So we really use this to check the answer to part B, but you get the answer to part B just by using the definition of entropy change. Make sense? Let's move on. So, yes, sir.
What can we conclude from the change in entropy?
Change in entropy being negative?
Well, in this case, it's positive from that.
No, it's negative. I just forgot to put the negative sign in there. It's a negative change in entropy. Because we just talked about entropy went down. S2 is lower than S1. Right? And we conclude that it was transferred out with heat. This is our first inkling. Oh, we're going to have an entropy balance. It's going to be generated when we have friction. It'll just come up it'll be generated when we have friction. If you have no friction, internally reversible, zero generation of entropy. But then you're going to have entropy balance. We'll have to account for any transfer of entropy with heat. And we're going to find also, just tell you, work, there's no entropy transfer with work. There'll be energy only transfer with work, but no transfer of disorganization with work. Work is an organized energy transfer. Heat at the molecular level, things are hotter, more energy content, internal energy content, more disorder. And when it's transferred, it transfers its disorder. That's a lot to swallow on the first day, isn't it? On entropy. What? Oh, I looked up in the table. I didn't look up, but this is Psat at 160. I didn't write it down. I don't know what the saturation pressure is. Yeah. All right. So now, entropy change for an incompressible substance. If you assume constant specific heat, here is the result. What? So if I have a chunk of copper and I say, what's the entropy change for copper during the process, where maybe it started at temperature 1 and it ended at temperature 2? I can use an analytic expression. No need to go to the tables. There it is. The only thing I need to go to the tables for is to get the specific heat of copper. Okay? But how did this equation come about? Well, you can use a couple ways. Let's do it this way. Take a look at both of your TDS equations. TDS is equal to du plus PdV, as well as TDS is equal to dH minus VdP. True? If it's an incompressible substance, does that mean temperature is constant during the process? Pressure is constant during the process? Internal energy is constant during the process? Specific volume is constant during the process? Entropy or enthalpy is constant during the process? What does it mean when I say it's an incompressible substance undergoing some process? I ask that question because I know it's tough. Right? Some people will say pressure is constant during the process with an incompressible substance. Somebody says, no, it's specific volumes constant. Those are the two big contenders. I don't think anybody will say temperature's constant, internal energy or enthalpy. It's whether or not its specific volume is constant for the incompressible substance, or its pressure is constant during the process. Have you made up your own mind? Yep, that makes sense, but did everybody process it in your own mind? Specific volume is constant. It's incompressible. Volume, no matter if I boost the pressure, the volume doesn't change. So, if I look at these, should I use the first or the second starting point? Because the pressure changes or because the volume changes? So which one should I start with? Well, V is equal to a constant. If V is equal to a constant, what's dV during the process? 0. So I'm able to strike some term. Can I strike the dP term? No, the pressure can go up or down. Can I strike the dV term? Let's use the first equation. Okay? All right, so we can use the first equation. If you use the first equation, you find that the T ds is equal to du. That sure doesn't look like that. How are you going to get to there? Okay, give me a minute. How about this? ds is equal to 1 over T du. All right. For an incompressible substance, how is du equal to? Is that equal to C dt? Is for an incompressible substance, is a change in internal energy equal to specific heat times change in temperature? Thumbs up, you agree? Only a few thumbs. Professor, we're tired. Is this good? Then what we can do is we can say 1 over T C dt, ds. True? It's already been separated. I'm ready to integrate. And now we integrate. Now the question is, if I have constant specific heat, what can I do with that C? Come outside the integral. Okay, the integral of 1 over T dt. Natural log. And so we integrate from the initial to the final, from initial to the final, from initial temperature to the final temperature, from initial entropy to the final entropy. So we get S2 minus S1 is equal to C times the natural log of T2 divided by T1. I know I can do it in a couple steps. Remember, the natural log of T2 minus the natural log of T1 is equal to the natural log of T2 divided by T1. So I use that, right? Guess what this is? We just derived it. How do we derive it? Starting with the TDS relation. Where'd that come from? Don't ask me. It was a combination of first law and definition of a change in entropy. Okay? It looked like magic hocus pocus. But there it is. And so you want to calculate the change in a piece of lead or iron or copper in a system that's going from hot to cold. This is how you do it. Or cold to hot, right? Let me ask you this. If I change the pressure, P2 is not equal to P1. Does the pressure have an effect on the entropy change of copper? Nope. So the entropy change is a function of temperature only for an incompressible substance. Let's go on to another type of substance. What type of substance? Ideal gas. We'll do the same thing. We'll say assume constant specific heats and get this relationship. But before we get knee-deep in the derivation, look at the equation. What does it tell you before? Think about the equation we just had up there for an incompressible substance. S2 minus S1 didn't depend on P2 or P1. Does this equation depend on P2 or P1? It does. This throws students for a loop because they'll be like, They think that the entropy change is only a function of temperature. For incompressible substance, you're right. Steam, you're wrong. Ideal gas, you're wrong. All right? It's a function of temperature and pressure. Okay. That's an observation. Please make it. Take a look at the pattern here. C sub P natural log T2 over T1 minus R natural log of P2 over P1. Do you know what this C is? Specific heat constant, pressure. The temperatures, do you think they have to be absolute or can they be degree C? They must be absolute. They must be absolute. Okay, I failed to emphasize that back here. Can that temperature to be degree C? No, just put in the temperature 1 to be 0 degrees C and throw it in your calculator and find out what happens, right? Is it going to be happy? Your calculator going to be happy? Can you have something at 0 degrees C? Copper at 0 degrees C every day? Well, not every day, but yes. It can definitely be cold. So why is that absolute? Why does it have to be an absolute? Because when you come back to this TDS right here, that is an absolute temperature. It is definitely an absolute temperature in the derivation because we used del Q over T is equal to ds. It has to be an absolute temperature. All right, how am I going to drive this equation? Start with one of the TDS relations. Which TDS relation would you like to start with? TDS is equal to du plus pdv, or the second one, TDS is equal to dh minus vdp. Second one is the winner. Why? Because three things I recall for an ideal gas. One, PV is equal to RT. U is a function of T only. H is a function of T only. True? And also C sub P is the rate of change of H with respect to T holding pressure constant. True? When I apply that, I find that dH is equal to C sub P dt for an ideal gas. dH is equal to C sub P dt for an ideal gas. All right. So it looks like I need some C sub P right there. It looks like this term is going to be C sub P dt. Starting to look like it's matching up. Okay, minus V dP. Okay, take this equation and solve for V and substitute. Would I get RT over P dP? Does that make sense? Good. So we used this one, we used this, then we used that, and we used that. Okay, all to get to right there, then we substituted. So here we are, TDS is equal to all. Does that all look good? What should I do next? Divide by T. ds is equal to C sub P 1 over T dt minus R 1 over P dP. You're there already. Can you see it? Now you do the integral. And you do the integral, the specific heat comes outside. You do the integral. Why does the R come outside? It's the gas constant. It's in the name. Constant. It's not a function of pressure. I put that on a first exam, or maybe something like that. Is R, the gas constant, a function of pressure? Sometimes. Never. 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 So it comes outside, so we like that integral, and then we're left with S2 minus S1 is equal to C sub P natural log T2 over T1 minus R natural log P2 over P1. Boom, there it is. That's our equation. They just emphasized that this is a function of temperature and pressure. That's a function of temperature and pressure. They could have just put S2 minus S1 on the left-hand side. It would be just as good. They're just making sure to emphasize it's a function of temperature and pressure. Okay? Makes sense? Did you know a little bit of work you can get another equation that S2 minus S1 is equal to C sub V natural log T2 over T1 plus R natural log V2 over V1. I'm not going to do that work. It's easy. But I can see by the yawns that some people are having a hard time staying awake, huh? No? Okay. But this is the pattern here. Now, what is the restriction? Ideal gas and specific heats are constant. Somebody will say, I like this equation. I'm going to apply it to steam in a two-phase dome. I'm hoping for a lot of partial credit. Don't do it. Don't do it. Don't do it. Please don't do it. Okay? It has restrictions. Just like this equation has restrictions. Incompressible. Constant specific heats. True or false? The internal energy of an ideal gas is a function of temperature and not a function of pressure. True or false? Enthalpy of an ideal gas is a function of temperature and not a function of pressure. True or false? Specific heat, constant pressure of an ideal gas is a function of temperature and not a function of pressure. All of those equations are either all true or all false. It can be a constant function of temperature, but if you do have a more complicated ideal gas molecule, that's when you do get that temperature dependent. If it was a monoatomic ideal gas, it's flat line. C sub P is it's just a constant. It's not even a function of temperature, but at most, it's a function of temperature. Guess what? He's finally getting to. Okay, forget that one. Get down here. Entropy of an ideal gas is a function of temperature and not a function of pressure. True or false? And it'll trip up students all the time. This is false. And what happens is they think that they got so used to, it's an ideal gas. Only a function of temperature for internal energy. Only a function of temperature for specific heat. Only a function of temperature for enthalpy. Entropy, ideal gas, only a function of temperature. I guess that, right? Right? No. It's a function of temperature and pressure. We saw that in that last expression. All right. What if you have variable specific heats for an incompressible substance? Somebody says, great, you did it assuming constant specific heats. Give it to me. Give me the equation for variable specific heat, temperature-dependent specific heat. Well, you've got to go back to that integral, that equation, right? So you have S2 minus S1 is equal to the integral of C over T dt. Leave the C inside if it's a function of temperature. Do the integral. You have to tell the expression from 1 to 2. That's about as far as we can take it. What do you think the next question is? What happens if you have variable specific heat for ideal gas? Well, we had the equation S2 minus S1 is equal to the integral of C sub P over T dt minus R natural log P2 over P1. So I can't pull this outside if that specific heat truly is a function of temperature. I'm stuck. Guess what? Air tables. Did you ever use the air tables for looking up enthalpy, internal energy as a function of temperature? all they really did was they integrated that C sub v dt and that integral C sub p dt, right? They did a better job of accounting for how the temperature-dependent properties of air at elevated temperatures, how they depend, how they move, okay? Guess what? This is how they have accounting for the temperature-dependent specific heats in the air tables. So for air, you'll have S2 minus S1 minus, equal to S2 naught as a function of temperature only, minus S1 naught as a function of temperature only, minus our natural log of P2 over P1. This is a very difficult equation for students to swallow. I know I'm throwing it at you real fast, but these are in the air tables. And they give you how the low pressure, that's this naught up here, atmospheric pressure, low temperature change in entropy of air accounting for specific heats is handled. Here's our air tables. Here's temperature. This accounts for temperature-dependent enthalpy, internal energy. What is that naught? That was that term in that analytic expression, and it helps account for the temperature-dependent specific heats for the entropy calculation. Why the superscript naught on S naught? Why? Because it's at atmospheric pressure. It's at low pressure, okay? It's why not on H naught? Why don't they put H naught? Hey, you got it. Why not put a U naught? Because H is only a function of temperature for air, ideal gas. You see, this is ideal gas properties of air. It's assuming that air is behaving as an ideal gas at that pressure and temperature. And so they don't have to emphasize it, but here that has to be emphasized because to calculate S2 minus S1, you take the temperature dependent and then you have to include, and don't forget, this term. That's the pressure dependence, how it affects the pressure. So, okay, so here's temperature in Kelvin, H and U in kilojoules per kilogram, S naught kilojoules per kilogram Kelvin. They tell you the units up here. What about these two extra columns? Glad you asked. We'll talk about that later. Here's the equation. I didn't really need to rewrite it, did I? It's written, typed out right there. Make sense? Think we're done. So we are going to now talk about your exam.